Okay, 5.3, sinusoidal functions in the various, just one form, the basic form that explains all of the transformations. You can use it for a sine or a cosine. Both of those are called sinusoidal functions because sinusoidal function just describes any function that repeats itself over a period length. Okay, so the first thing to do is quickly review the possible transformations that you have already learned about in your investigations yesterday and the day before. And so jot down what these parameters do. What effect does changing A have on the graph of sine or cosine?
It's vertical stretch or compression.
Good. Vertical stretch or compression by a factor of A. What else can it do?
Can trying to think of the right word for it. Can reflect the function along the x-axis.
Yeah, we would say reflection in the x-axis. It's probably a better way to write it. You probably don't need the vertical reflection. It's a reflection in the x-axis. It could be if it's negative, right? What about K? Well, K is a multiple inside the sine. So whatever angle X is, if you have that K that's a multiplier, it's going to be a horizontal stretch or compression. And this part's important, by a factor of 1 over K. It can also give you a reflection in the y-axis. Then we have our translations, D and C. This is going, D is with X inside that bracket, so whatever X is, it's going to add or subtract things to move it left or right. So D is a horizontal translation. Horizontal translation by D units, I suppose you could say.
I think in functions, like in grade 11 functions.
Oh yeah.
You said the right term is like phase shift.
That's right. We do the phase shift. You could leave that word in there, horizontal translation. That's fine. But we also call it. It's a phase shift because it's a never-ending. It's a never-ending function, so it doesn't actually move really. It's not like you're picking something up and you're moving it, but you are shifting it along the pattern somewhere. Okay, and then the whole thing from negative infinity to positive infinity will shift, but it will continue to be infinite. Phase shift. Okay, good. C. This is a vertical translation by C units. If C is negative, it moves down. If C is positive, it moves up. So now we take that and we're just going to work on some transformations of sinusoidal functions. So example 1 we have there is transform the function f of x equals the cosine of x to g of x so that g of x has these characteristics. It has an amplitude, and I'll just write down what we have here. It's going to have an amplitude of 4. It's going to have a period of pi. It's going to have a phase shift of pi over 6 left. And it's going to have a vertical translation 2 up, 2 units up. So basically we're going to look at each of those things and what does it tell us about the parameters a, k, d, and c. So amplitude is half the distance between the max and the min, and it directly translates to the value of a. So a equals 4. Okay, we're not told that there's a reflection or anything like that, so we know it's just positive. The transformed function is going to have a period length of pi. That means, well, what's the standard period length of a sinusoidal function?
2 pi.
It's 2 pi, okay? So basically what we need to find out then, we know that period is equal to, well, the period length that we have is equal to 2 pi over k, okay? Because that's where we get this part in, that's compressed by a factor of 1 over k, okay? So we know it's being compressed, so we put the full period length over k and we say, okay, what has to happen in order to get us a period length of pi? So,
Equals 2.
yeah, so 2 divided by 2 is, you can think of this a couple of different ways. You can think of it as a division triangle, okay, where 2 pi is up here and you have pi and k. And so 2 pi over k equals pi. Pi times k equals 2 pi. So what does k have to be if pi times k is 2 pi? Well, k has to be 2. Okay. If you want to, you can multiply all that out. You could if you want to do it algebraically, you could multiply both sides by k. You'd end up with k pi equals 2 pi. And then you could divide both sides by pi, and you'd get k equals 2. Now, k equals 2, but what does that result in? This results in a horizontal compression of 1 over k, which is 1 over 2, okay? So this thing is going to be compressed. It's going to take up half the distance horizontally that it normally does. We know that because it went from a period length of 2 pi to a period length of pi. But in that, to do that, k, the value of k is 2, okay? Phase shift is pi over 6 radians to the left, so that tells us d. d is going to be negative pi over 6. It's just our horizontal translation. And our vertical translation, c, it's going 2 up, so c is just positive 2. Now all we need to do is, in our general case, which I can write down for us, a times the sine of square bracket k x minus d, close it off, plus c. All we need to do is take the information that we found out here and sub it in the correct place. So g of x is equal to a is 4 times the sine of square bracket k is 2 x minus d, where d is pi over 6. Sorry, negative pi over 6, which means we end up with a plus sign in there. So x plus pi over 6, and then we're going up 2, plus 2. Okay, so always double check it back with the general form. The two tricky things to look out for is k. So yes, it's a compression of 1/2, gives us a k value of 2, and 1 over k. And then the negative sign in the brackets here. So d was negative for us, so we ended up with x plus. X minus negative pi over 6 is x plus pi over 6. Okay, so again, getting those characteristics and then just subbing it into the general form. Next part says graph it over at least 2 cycles. There's a couple of different ways to do this. One of the easiest ways is to kind of do it in chunks. So you're going to start by sketching a cosine curve. And some things that you already know about it is that it has an amplitude of 4. Okay, so I'm going to scroll up here. We're going to do 2 cycles. Basically, you need a standard cosine curve that has an amplitude of 4. So cosine has its max at 0, 1, but we'd be going up for an amplitude of 4. We'd be going up to 0, 4 for its max. Okay, it crosses, again, it would have, and actually I think we want to change the period as well, okay? So we're actually going to already change the full period length to pi instead of 2 pi, so that by the time you get to 2 pi, you would have 2 period lengths, which means that you're going to have another max about there, and another max at 2 pi, which means your minimum is 1, 2, 3, 4 down here at -4, and it's going to be at pi over 2 and 3 pi over 2, and then we can draw that curve. Okay, so it's pretty steep. Keep in mind it's always rounded at the max and min points. Okay, that's going to help you really draw a better, more accurate curve. It doesn't hit a point and come down, it is rounded. Alright, there's 2 cycles. I can add a little bit just to give me a better reference, and I can go, it doesn't say where those cycles need to be, okay? So you could also keep going and go down into -pi, in which case you'll be back at your max. So going down, there's my min. All right, good enough. We've got more than, we have 3, 1, 2, 3 full cycles there. So the first thing that we did was we graphed, and I'll draw it in blue because that's what we did, y equals 4 times the, and I lied already right from here, we're not even using the sine function, we're using the cosine function. So in your answer there, if you...
Is that not the cosine function?
Yeah, but I didn't write that in when we did all our work. So just make sure you did that. We're doing 4 times the cosine of 2x. Okay, that's what we've done so far. And now we're going to do the next step. So now we're going to apply a phase shift of pi over 6 radians to the left and a vertical translation of 2 things up. So now the graph is not changing shape anymore. It's just getting translated. It's just moving. So I'm going to move everything pi over 6 to the left. So if this is 1 full pi, then pi over 6 is like maybe this. Okay? So I'm going to move all of my points pi over 6 to the left. I do that for all my maxes, all my mins. You can even do it for your x-intercepts if that's helpful. Okay? Basically just giving yourself a bunch of new points to reference. Yours will be a bit more precise because you have your grid there. And we want to move every single point 2 units up. So take your max and move it 2 units up. It is helpful to have multiple colors, especially now because I'm going to run into a situation where I'm not going to really know which dots to follow. I could erase my old dots. Alright, and I'm going to try to draw this thing out. So I've got a, from the rest, doing my x-intercepts was maybe a bit much. Should just stuck with my max and mins. But either way, looks okay.
You're probably not going to look back on it because it's not like in your note papers. So
So I won't be bothered once I erase my whiteboard.
yeah.
Okay, so the pink one here, that's our final. We always want to name the graphs that we put on a graph. So there we go. That is our transformed function. And not sure why I'm writing y. It's g of x. And there you go. Okay, do it step by step. We applied our multiplication, our factors a and k first when we drew it. Okay, you have to do that. You have to do the multipliers first, the stretch, compressions, reflections. Then you can take that shape and move it wherever it says to be moved. All right. Okay, example 2, we have another transformation of a sine function, but this time the data, the criteria that we're given is not given in terms of pi, okay? It's still in terms of radians, but it's not given in terms of pi. So we're going to follow all of the same steps. You have a list of criteria in front of you. You have an amplitude of 2, period of 1. You have a phase shift 0.5 radians, and you have a vertical translation of 3 units up. Okay, so we go through that. We get our A, K, D, and C. Amplitude's easy. It's 2.
For a period, we can put 2 pi, and then it'd just be 2 pi over 2 pi. And that'd give us a period of 1.
It's K, yes, correct. So do you guys have a little note there? Since the period of the sine of x is 2 pi, you have that note on the right?
Yeah.
Okay, we need to find k such that the period will be 1. So you simply take 2 pi and divide it by 2 pi, and you'll get a period length of 1. Okay, so k is 1. Sorry, k is 2 pi. Huh. K is 2 pi. Phase shift is our value of d, and we are moving to the left. So d is going to be negative 0.5. And c is a vertical translation 3 up, so c equals 3. Then we just take those, we sub them into our standard equation, and we get g of x is 2 times the sine of, now look at k, k is in terms of pi, 2 pi times x plus 0.5 plus 3. One reason why this one is tricky is because now inside this bracket, x is an angle, a radian angle. So all of the radian angles that we know or have used most, they can be just numbers, but often they're in terms of pi. But now look, you're just adding a number to it. But what you have to realize is that this is still the angle. Okay, inside there is still the angle. And over here you have something in terms of pi, which can be tricky. We might think, oh, that's the angle. No, that's k. That's the horizontal multiplier there. That's going to be the stretch compression factor of 1 over k. Okay, so don't get tricked by that. If the angle is, or if the criteria is not given in terms of pi, you might end up with a pi over here. That's fine. Pi is just a number. Okay, it's just an exact number. And we could sketch this one as well. Again, you would start by graphing y equals 2 times the sine of 2 pi x. So that's your vertical stretch, giving it an amplitude of 2. A horizontal compression, giving it a period of 1. And then we'd go from there. And actually, if I were doing this, I wouldn't put numbers on my axis yet. I would just graph a curve, a sine curve. Try to make it perfect. Try to make it look like standard sine curve. Okay. Standard sine curve goes through 0, 0 on its way up. So then I would put in my vertical axis. And here's my max. And I know my amplitude is 2. So I'm going to call that 2, which makes that 1, which makes this -2, which makes this -1. And I know my period length is 1. So that means 1 is right there. And 1, 2 is right there. Okay, it's a lot easier most of the time to draw a nice curve and then add your axes and your scale, your numbers along your x and y axis. And then from there you can translate it. You can move it 0.5 to the left, and you can move it 3 up. That's not that hard. We'll just take any point. We'll take our x-axes, x-intercepts, and we're going to move them 0.5 to the left and 3 up. So there's an x-intercept. I'm going to take my maximum point, move it 0.5 to the left and 3 up. Take this point, 0.5 to the left and 3 up. I'm just kind of guesstimating, but you guys will be a bit more accurate. 0.5 to the left and 3 up. Take my minimum points, 0.5 to the left and 3 up. Point 0.5 to the left, 3 up. And see what kind of curve we end up with here. Pretty ugly.
It's very dynamic shape curve.
This is super sloppy.
Why does it look flipped? I don't know.
Yeah, so no, that is a good question though.
Yeah,
You will find that shifts can look like flips and flips can look like shifts and vertical stretches can look like horizontal compressions and all that starts to happen. I think we've got 2 full cycles there. Good. Okay, the next one is about a carnival ride called the Roundup. It goes round and round and round and round and round and round. And it tilts also. So it has a relationship between time and height. It also has a relationship between the angle of rotation and height. So what makes this a good, how come we can apply a sine curve to this thing? What makes it sinusoidal?
Well, like a function's obviously going to have sine x as
Why? Because the sine
repeats
function
itself.
repeats itself. Nice.
Oh, that's
Okay.
what you're looking for.
It repeats itself. It's going to be at the same height over and over and over again, and it's going to continually change with respect to an independent variable time. Okay. So what we're going to do is we're going to determine a sine function to model as a model for the vertical position, that's the height, in meters of a rider on the roundup after t, that's time measured in seconds, following the specific criteria here. Okay, so what are we doing? Well, we're going to model using the form h equals a times the sine of k x minus d plus c. We are told that the maximum height above the ground is 7.5. Do you guys have little notes in your book at all?
Yeah.
Little like in brackets? Amplitude is half the, yeah, you have all that? Okay, good. So we're told that the maximum height is 7.5 and the minimum height is 1.5 meters above the ground. And amplitude is half the difference between the max and the min heights. So we have the difference between the max and min heights, and we're going to take half of that. Okay, that's going to give us its rest position. Sorry, that's not going to give us its rest position. That's going to give us its amplitude. So here we have 6 over 2, which is 3. So we have an amplitude of 3. Then what else do we have? It's going to, one full rotation takes 5 seconds. One full turn takes 5 seconds. So we know the desired period length is 5 seconds. So period length equals 2 pi over k. Multiply both sides by k. We get 5k equals 2 pi. Divide both sides by 5. We get k equals 0.4 pi. Okay, we're doing well. Now we need to figure out what its phase shift is. So we know that the maximum value on the standard sine curve, or any sine curve, occurs at 1/4 of a period length. Okay, so let's say here's our y-axis. Okay, and if we go, here's a 1 full period would get us to here. So 1/4 of that period length brings us to our max. Well, we're going to use our new period length of 0.4 pi to calculate where this maximum should occur, and then we'll know exactly how far to move this thing left or right, okay? So in this case, 1/4 of a period, if a period is 5 seconds, okay? In this case, here we go. We'll say, maybe take a few notes if you have a little bit of space there underneath the bracketed. In this case, 1/4 of a period is 1/4 times 5, which is 1.25 seconds.
Wait, do you want it to start at 0?
Sine curve?
No, the d, or well, we want the function at 0 to be 0, no? Or am I missing something here?
Well, we're told when it reaches its highest point. In this case, the model, on our model, on the carnival ride, you're going to hit your highest point at 0 seconds, but that's not true of the standard curve, standard sine curve, okay? It hits its highest point at 1/4 of a period length. So first we figure out what is 1/4 of a period length. And now, since we know that we want that to occur at t equals 0, now we know how far we actually have to move it. We have to move it 1.25 left. Does that make sense? So we have to move, the sine curve has to get moved in order to match up with our criteria. It has to move 1.25 seconds left. Okay? So let's look at that again. So in our model, the highest point is to occur at time equals 0 seconds. So in order to do that, we're going to take we're going to find out how far we need to move this thing. So you have t minus d, and that's going to be 1.25, because that's what we found out as where the maximum occurs. The time, the start time that we are interested in, we want this to occur at 0. Okay? So now if we set that, then calculating this out is going to tell us exactly how far we need to move this thing in which direction. 0 minus d is negative d. If negative d is 1.25, then d equals negative 1.25. Okay, so that's algebraically. We had already kind of explained that if you have this sine curve and you want the max to occur not here, you want it to occur right here, okay, then you are moving this thing. That's a phase shift of 1.25 left. So you can think about it this way and then get your d. You know that translates into a d of negative 1.25. Or you can do it algebraically using this strategy. Okay? Either way will work. Last thing that we need is our value for c. The vertical translation, that is the new rest. You're moving it up from a rest of 0 to wherever this rest is. Obviously, it's not 0 because this ride can't go underground. Okay, it can't have a negative height. That would be disastrous. Okay, so C then is the average of the max height and minimum height. Okay, so
amplitude.
no, it's different. So amplitude is the difference divided by 2. The rest, you add up the max and min
Oh, okay, yeah.
and divide by 2. Okay, so you end up with 9 over 2, which is 4.5. Good. We just take this. We take our standard function here, drag it all the way down. We fill in what we just found out. The height of the rider with respect to time. We can even use t instead of x. The height of the rider with respect to time. A is 3, amplitude of 3, times the sine of, square bracket, k we found out was 0.4 pi, round bracket, t is our independent variable, d is negative 1.25, so we have t minus negative 1.25, that's t plus 1.25. Close that off, square bracket, and we're moving this whole curve up 4.5 meters, 4.5 meters. So the addition to this problem is this. This is really important. Okay, the max of the sine happens at a quarter of its period length. What's the period length? So according to our structure, this carousel ride or carnival ride, the max is going to happen after 1.25 seconds. But by the criteria that we're given, the highest point is actually going to be at 0 seconds. So we need to take the curve that we have so far and we need to move it to the left 1.25 seconds. You can see that graphically here. You see it algebraically here.